like to call the other 90%. That is to say, the students who don't and maybe aren't going to identify as formal methods people, but who, like it or not, might be writing the next chat software that OOPSLA is going to use in 2030. Something very dear to my heart is they might also be writing the software running an airplane or an air traffic control tower that I'm going to use to get to and from OOPSLA in 2030. So we should all really care a whole lot about the other 90%, even if they can't do a Dijkstra proof. Being able to answer questions like, what's the invariant? Being able to think precisely about their threat model, their assumptions, to model their systems rigorously, even if they can't prove them correct. In fact, I go so far as to say I don't care about proof with respect to those students. And this is where the tools really start to matter, the tools that we provide to these students. I'm going to give you a demo using a tool called Alloy. And here's the deal. If you're unfamiliar with Alloy, don't worry about grokking the essence in full of the syntax. The key is that I have a specification here that's meant to sort of express what I think a binary tree is. I have a notion of nodes. I have some constraints that talk about connectivity. And I can also add a property, a requirement that says, hey, I think if something is a binary tree, it ought to have a unique root. And the key about Alloy is that I've got an execute button. I can run this requirement. And the solver underneath will return an example. In this case, a worrying counterexample. Maybe I didn't encode the notion of binary tree correctly. Alloy, tell me what I did wrong. So Alloy's going to pop up this image here. And I can't look at it in great detail because of time constraints. But I'm already pretty worried. That's not a binary tree. I can do better. OK, so let's say that I do better. I'm going to add a couple missing constraints to my Alloy specification. I can rerun, and now Alloy's going to tell me no counterexample found. What does that mean? That means that there is no counterexample up to the bound that I have selected, thinking back to the keynote from Wednesday, right? Bounded model finding. In this case, 7 nodes. So this is not a proof. There is no theorem being proved here automatically or otherwise. But there is a solver-based exhaustive search that has really increased my confidence in my specification. But it's not just about verification. Here, I've got just the specification. I can run it by itself. I can say, Alloy, please show me examples of what I think is a binary tree. This is the version before I fixed the bug. And I'm going to get an example. And I'm already really alarmed before I even think to write that property. So this kind of tool ends up being really great for design space exploration and other similar activities in addition to verification of properties you've already got. Key takeaways. Alloy provides automation, push-button automation, i.e. the student have a rapid development cycle that may well echo what you get in an IDE for a programming language. It supports more than just verification. We're going to get to that a little bit later. Keep that in mind. And it provides this automatic visualization. Right here I am modeling a directed graph. I get a directed graph. Again, I've been teaching Alloy for about a decade. More than 1,000 students have passed through my class. I've graded more than 1,000 students. And I love Alloy. It is wonderful for all these reasons. But like all things, it is not perfect. And so over these 10 years, we have recognized a few shortcomings, specifically when it comes to education, Alloy for education. The first is the language is too complex. There's a great deal of syntactic sugar, and a great deal of the language relies on or refers to relational algebra, which my students at least might not know much of, and I would wager that many of your students don't either. The visualization is quite inflexible. If what you need is a directed graph of a particular style, it's great, it's perfect. But not everything you want to model and reason about can be visualized as a directed graph. And finally, students will come into their first formal methods course, if they're not formally inclined, knowing exactly one formal method, that is to say testing. And it's important that a tool that's trying to interface with such a student's state of mind is able to help them carry over that intuition for testing into thinking about more formal specification. Thus, we have created a tool called Forge, and you can think of Forge as Alloy for education, specifically for the other 90%. The way that we respond to these issues is first, we add language levels that provide a scaffolded progression of expressive power to match the progression of student skills. We provide custom visualization facilities. And we provide some new testing constructs to help scaffold that evolution from unit testing in programs to formal specification. In the interest of time, I'm only going to talk about the first two here. So, hey, let's get started. Let's talk about language levels. Deal with language levels, right, is that they enforce limitations on expressive power. They are constraints. They are seat belts. Those of you who have taught using Racket may be familiar with this in the sort of the fundies or 101 context. Here's an example of why language levels exist in Forge. So this is an Alloy sentence, an Alloy formula, and it's saying everybody's at home right now. Right? For all person, that person's location equals home. The syntax it's kind of friendly. That dot looks a whole lot like field access. It looks like we're doing object-oriented programming, maybe in a language like Java, maybe in some other language. But, oh boy, under the hood, that dot is relational join, and the location field is actually a binary relation that witnesses the connection between persons and their current location. That means that in Alloy, you can write something like this. I will pause for a moment while you consider that. We're not doing field access anymore. But it turns out, if location is constrained to be functional, that these are equivalent. And students, especially precocious students, boy, do they have a pattern of discovering this at the least opportune time, getting confused, and ending up with really, really tangled bugs. So how do we solve this? Right now we have a progression of 3 languages. The first is a basic language that we call Froglet. All you get is functions and quantifiers and Boolean logic and stuff like that. You do not get relations yet. So I can talk about nodes having at most one left or right child. I can talk about a node having no ancestor or having an ancestor, but I can't exercise the fullness of the power of relational algebra yet. Interesting to note that even though for us at the time our students are picking their own midterm project and implementing it, at that point they've already seen the next language level for a couple of weeks. Many of them still choose this language level and still use it to accomplish some pretty extraordinary things. Then, of course, we add the relational operators back in. Students have the experience with quantification and other basics. Now they're ready to wrestle with things like relational join and transpose and so on. So oftentimes this comes up as soon as students need to model a directed graph that is weighted. You need the ability to talk about sets of edges. You need the ability to talk about unrestricted transitive closure, to talk about how to sort of use join to strip off the weights so that you can get the unweighted connectivity relation, and so on. And then finally, just like in Alloy 6, we add linear temporal logic to the game so they can start talking about traces more easily. So here's an example from dinner. We have some philosophers, and they're going to be dining. Maybe they've got some chopsticks or not. I don't know. That's going to vary over time because those fields are marked as var. And when I write my constraints, now I have the fullness of linear temporal logic available to me. I can talk about safety and liveness in the context of these operators rather than in the context of sort of I'm trying to quantify over state in particular ways. All right. The key here is this is just Alloy syntax. We weren't the first people to think of adding linear temporal logic to Alloy. But it's not just about syntax. Let's say that I want to model people and places, and people have a notion of how old they are in this model, places do not. So if I write a constraint that says LA's age is 5, I ought to get an error message. The question is, what error message am I going to get? If I'm in Alloy or Relational Forge, the assumption is that the user is going to be able to understand what it means. Join always results in an empty relation. Because there's a mismatch of types, that join can't ever join up any tuples on the left and the right-hand side of the dot. But if you're a student who doesn't know about relations yet, this can be a problem. If you're in Froglet, the abstraction students get is one that is focused on the abstraction that Froglet provides. This is the epistemic closure idea from language levels you might have seen elsewhere. All right, let's talk about custom visualization. I want to maybe give you an exercise. I apologize for doing this, but there was just ice cream and I didn't have any, so I'm jealous. So I want to ask you, what is this an example of? This is an unfair question. I apologize again. Let's zoom in. What domain do you think we're modeling? Any guesses? I'm not gonna call in any brown people. Spoilers. Yes. It's the dining philosopher's problem again. I like the dining philosopher's problem, except this time they're eating with forks rather than chopsticks. Okay. Great. Awesome. Okay. So dining philosopher's problem, a state of that problem as a directed graph. So here's that state again, and you can sort of think of this as being the pre and post state in a transition in the dining philosopher's problem. I'm going to ask you, what has changed here? What's the diff? I know that it's unfair. This is very small. The screen is very small. That's not the point. So some of you are seeing like the addition of a new arrow. Absolutely, a new arrow got added. That's the thing that's about the dining philosopher's problem right there. That's insightful and semantic. Here's another picture. It's got a table and it's round, and there's even some kind of weird shaped forks. So here's a post state. What's the difference? What's changed? Somebody picked up a fork. Somebody picked up a fork. It's the same picture. Those are the same states. It's not just about pretty pictures. Custom visualization is not about graphic design, although that's a noble calling. It's about communicating clearly. And sometimes the person you're communicating with, hopefully clearly, is you because you're trying to debug your model or develop your model. Okay. I want to show you one more example. So this is the default visualization for a crypto model. This is a model of the Needham-Schroeder authentication protocol. But wait a minute. People who study crypto have domain-specific visualizations that work very well for this. In fact, you might be thinking, why not just have a sequence diagram? So sometimes it's not just an amorphous sense of clarity, but really about a shared set of visual syntax among people who are familiar with the problem. All right, so again, why custom visualization? These standard visualizations exist. Another factor which I think is interesting is if you're teaching, probably the textbook has some visual language that it uses for a concept. And if you're giving your student a visualization, you'd really like this to match. And then finally, all the reasons why clarity is important for the development of the model, not just the presentation. Okay, you want to know if Forge works. I'll tell you if Forge works. So what do students reason about? They propose their own projects in my class and execute them. So you get the usual computer science topics. You get puzzles and games. Some students decide to learn about cryptic structures so they can do epistemic logic puzzles. That's fun. You learn a lot watching your students try to model baseball and Minecraft exploits. You get some mathematically inclined students who want to model group theory, like check the first isomorphism theorem, that sort of thing. And you even get people from physical science modeling concepts from chemistry. So does Forge work for students? I'll let the students speak for themselves. This is what success looks like to me. So in short, Forge is available. You can go, you can give it a try right now. I hope that you do. If it works for you, please let me know. I want to talk to you. And hey, if it doesn't work for you, if you think it's bad, let's talk. I extra want to talk to you then, because this is continuing in development. There's going to be another 27 undergraduate researchers in addition to grad students and so on. There's also a book draft currently available. And I'd like to take your questions, but even more than that, I'd like to start a conversation on how we can make formal methods a thing that is for everybody. Thanks.
Let me start us off, and could the people who want to ask questions go to the mic at the back there. I encourage you to introduce yourself, and the mic is for the recording. Very cool work. So from the visualizations, I can see that students put in a lot of work into building them. And so there's some sort of background that they have. Could you talk about what that background is?
Sure. So at the moment, the way that you create custom visualizations is by writing a little JavaScript program. They are not tremendously complicated, but they are, however, JavaScript. This is one of the things I'm really working on right now because I'm teaching formal methods. I don't want people to have to know JavaScript coming into my class.
Hi, great talk. I appreciate that you used the dining philosopher's problem as an example too, because I did have that as a homework problem once. So I was wondering, I saw this was a question more related to the alloy thing, because I noticed that you give a counterexample when students make a mistake. Am I correct? So you show them through a counterexample how to get closer to the solution. So I was just wondering, because I did notice that you folks at Brown use a lot of example-based tools to teach students. I was wondering, how large can a problem grow before you can't provide an example back to a student, and what scale of problems can you use these kinds of tools on before it's kind of becomes impossible?
So the question is about scaling, and I think that there are two dimensions here which are both very important and very different. The first is the problem so big and tangled that the stat solver under the hood can't produce a satisfying instance or show unsat? The second problem is, how many of these are you going to get? Because if I'm in sort of design space exploration mode rather than counterexample mode, it's not a given if it's a subtle bug that the first thing that you see is going to be wrong. Right? We have some other work exploring that in disciplined model finding and trying to find the right instance to show people. Happy to talk with you about that offline. The scaling problem is, I'll say my students are able to model those kinds of topics, but one thing that both Alloy 6 using the standard backend and Forge are bad at is very, very long traces. Alloy 6 benefits from, there is an unbounded trace model checker in there, but that sort of is only specifically for that one particular kind of scaling. I'm still planning.
Awesome. Thank you so much.
Hey, thanks for the great talk. I want to ask a question about authenticity. So I'm wondering, do you, I guess at the start of your presentation, you very well convinced us that like introducing Forge into the classroom is a great thing. I guess my question is, are students convinced generally? Do you think that the students think that Forge is a weird thing they'll never have to use, or?
So that's a subtle question. Let me see if I can repeat it back to you. You tell me if I'm getting it right.
Okay.
So do students think that what they are learning to do in Forge will actually benefit them later in life?
Yes.
That's a slight rephrasing, because they do think that Forge is a weird thing, and they're not going to use Forge in industry, probably, or although some people use it in academia. That said, the things that you learn to do in Forge immediately apply, more or less, to Alloy. We cover model checking, we cover SMT solvers, right? So Forge is, think of it as the foundation that jumpstarts people into more advanced formal methods if they wish to use them. Otherwise, they can just model whatever they want in Forge.
Okay, cool.
Hi, great talk. I work in this idea of gradual verification, which is trying to like basically do incremental verification and specification, but we do it all in one tool, and so you can kind of basically turn off and on things at any level of granularity in one tool. But I noticed you kind of do that by having their own environments for each kind of like step in the formal methods process. So I was wondering if you have found that that's better, having it in separate environments so that students don't accidentally start using the other features, because in our spec language, basically all of it's there. You just don't have to use all of it.
Right. So this is sort of the difference between what Alloy does. Alloy encourages sort of three different styles, right? You can do it relationally, you can use predicate calculus, and they're all there. And Forge enforces. It's all about the error messages for me, because oftentimes we haven't covered something and then students don't know what to do about it. So the error messages, when you create a language level in Forge, you have the ability for every operator to specify language-specific errors there. And that, for me, is a big advantage for teaching.
Awesome. Thank you. That's very cool.